There are going to be two lessons today, and the first part is going to be kind of essentials, and the second part is going to be more advanced stuff, and some part of that advanced stuff is going to be also essential, advanced part, but another part will be kind of optional or additional. But overall, we have a lot to cover. We will start from looking at the Scala type system, looking at different kinds of polymorphism we can do in the language. We'll go through the data structures, collections. Then we will do different styles of error handling, how we can handle failures in Scala. Talk a little bit about purity of functional programming. What does it mean? About so-called, I call this like functional primitives, higher order function composition covering, lazy evaluation. And this is, I'm planning it to be like a first part. And the second part is going to be looking into for comprehensions and what lies beneath it. Then going through the monad, interesting word. Then looking at some functional design principles in the Scala language, in the functional programming overall. Then we'll go through the approaches to unit testing, implicits, and there will be a little bit more advanced topics in the end. Yeah, so this can be tough, I'm afraid, but I will do my best to make it as smooth as possible. So Scala is statically typed, that we learned previous time, and it plays important role in the language. It makes it really powerful, gives it a lot of power, and you can exploit this powerful type system a lot. And in that regard, you might remember last time I mentioned that some people even say that if program compiles, then it is ready to production. So it has a lot of sense in that words. And this diagram, this tree represents the edges of the Scala type system. So everything starts from this any trait, which is at the very top of the Scala type system. So every other type and every type you define, every class you define implicitly extends any trait. So, and under it, there are two kinds of things. Basically, there are any val and there is any ref. Any val is for all primitive types, but we know that there are no primitive types in Scala, like in Java, for instance. Everything is an object, but underlying and on the level of GVM, they are transformed to the actual GVM primitives. So all of the numeric types, Boolean, char, unit as well, extend any val interface. And there is an any ref. This is for reference types. And for instance, all Java types, all Java reference types, and all Scala reference types go under this interface. So, and your types, your classes that you define basically implicitly extend this any ref. And there are two interesting types which lie at the very bottom of the type system. So null is basically the type which extends every other reference type. So whenever you have some place where some place with specific type, you can specify the null instead, and it will work. So whenever there is a reference type, you can just put a null, and there is a null value in Scala the same way as in Java. And the nothing is the same, but it acts the same way, but for the whole type system hierarchy. So this is the bottom of the file system, no, type system, file system. Yeah, and just to revise a little bit about how what is the difference between this reference and value types. This is how the GBM memory model looks like. Maybe some of you are aware of it. So value types or primitive types in Java, they are stored in the stack memory. And stack memory is the memory of the thread. We will not go any deeper here about threads right now, but just remember that value types are stored in the stack memory, and reference types are stored in the heap. But references to those types are stored in the stack memory as well. So stack memory is a fast memory, and it stores references to objects which are created on the heap. Strings are a little bit works a little bit other way, but for primitive types, it basically works like that. So revise all of this. Any val, any ref at the top of the hierarchy, null and nothing at the bottom. So those are types basically. And for null type, there is a single null value. It's an instance of null. And actually, those two are not used very much. It is discouraged to use these types. In Scala, this is more to Java interoperability, I would say. And nil, as you already learned, it's an empty list, basically. And what else? There is no instances of nothing. Nothing, just a type. And this triple question mark we used a lot in our practice. This is basically a method which returns nothing type, but actually it just throws exception. There is no value for a nothing type. And the unit is just like a void in Java or any other statically typed language like Java. So this is mostly to be interoperable with Java as well. And whenever we have a method which doesn't return anything, we put unit. Yeah, so there is one more thing called none, but we will cover it later. Yeah, so there can be a lot of confusion if you don't know with this non, null, nil types in Scala. So let's talk a little bit about polymorphism. When you say polymorphism, you usually think about object-oriented programming. And in object-oriented programming, it is done basically with subtyping and overloading. So you have some three kind of inheritance of objects, and there is a common interface and different implementation for that interface. As yeah, so but this type of polymorphism is just a one, not even one of the types, it's one of the subtypes, I would say. And two main types, I would emphasize, two main types of polymorphism is ad hoc polymorphism and parametric polymorphism. So this object-oriented classic polymorphism is one kind of ad hoc polymorphism. But ad hoc polymorphism basically means that polymorphic functions can be applied to arguments of different types. Sounds a little bit abstract, so this sounds a little bit simpler. You just write different code for different types. And in case of parametric polymorphism, you write same code which works for different types. So this goes to people name it like generics, generic functions, generic data types, and generic programming overall. Yes, so this should be common to those who used statically typed languages before. So this is the way we do parametric polymorphism, one of the ways. This is a polymorphic function. And basically, as we can see, it is just a single implementation that works for different types for arbitrary type A. And usually, in such statically typed languages, all these types, generic types, are known only at compile time and are erased at runtime. So this is how it works usually, but there are some languages which preserve this type information at runtime as well. Yes, so let's just switch to our last session examples. There was a last function, and we'll just, where it was, give me a second. Yeah, no, I mean week 1. So we had this last function, yes? So just a small, a quick task for you to implement this function in a generic fashion, to add this polymorphism to that function. This should be simple. You can just post in Slack and we will go further if there will be no questions. Yeah, great. So this is just as simple as adding the type information in the function definition. Okay. Oh, what did I do? I stopped sharing.
Sorry, is there like default notation of generic type, like some languages we type T, we want to use generics. It's like, it's not required, it's just between developers.
What do you mean between developers?
Договоренность условно. Like instead of typing just random letters, usually
you mean naming convention?
We use letter T.
Well, yeah, it's just a convention.
Yeah.
Yeah, it's a good practice, I would say, to give them more refined name, more meaningful name. It's a good practice, and it's not used that much in other languages, but in Scala it's used more. People tend to give types more meaningful name, but in the case of Scala standard library and collection APIs, just T or A.
Yeah, because I saw examples where there just was A, B, C, D, and what's the meaning of them?
Well, where it makes sense, if this is some business problem context and this type describes some meaningful thing. In the case of such abstract things like library, Scala library, collection APIs, and yeah, it doesn't make sense. Yeah, but actually you can write, well, we will cover it a little bit later. There is the whole thing called type level programming. Okay, are there any questions at this point? Nice. By the way, I have something with me. I came prepared. So for good questions, I will, can you catch this? For good questions, I have sweets today. Nice. Why am I not sharing? Yeah, great. So besides having polymorphic functions, we can have polymorphic types overall. And you actually might remember that the function is a type itself. It's a class. It's an object itself, which is defined with a trait. So basically, we don't have like parameterized functions. We just have parameterized types. And for instance, in the last class, we did this integer q implementation, so we can switch really easy to the polymorphic definition of it. So this will work for any arbitrary type T. Okay, this looks great, but this type actually gives us too much freedom, I would say, in some cases. What if I want to put some constraint on it? So usually you can do, like in Java, in other statically typed languages, there is something called context bounds. So you can, in Java, it will be like T extends, if I remember correctly, there is extends for that. So this means that this will work for for arbitrary type T, but this arbitrary type T should be a subtype of any val. So in this case, we are defining the Q, which will work only for value types, kind of primitive types, yeah, numerics, Boolean, char. And this is this syntax is for upper bound. For lower bound, there is the same sign, but in a different direction. Yeah, so this means basically, so the type T should be a super type of integer, which gives us like two types, any val or any. Yeah, you can use both of them. You can use both of them. This is not the best example for the lower bound. There can be some better example when you have some hierarchy and it makes sense to have this lower bound. Yeah, so it may seem naturally when you define a queue of longs and a queue of integers, it may seem natural that you can assign the queue of integers to a queue of longs, but it will not compile actually. In the implementations that we used, it will not compile. And compiler will say that this type q int doesn't conform to expected type q long. And the reason that's happening is that actually compiler doesn't know that these two types are related. They are subtypes of each other. And for that reason, in Scala, there is a special syntax with a plus sign. And in this case, we say that Q of T is covariant. And what it means is that if there is another type, R, let's say, and R is a subtype of T, then the Q of R is a subtype of Q of T. All the things called variance, and there can be covariance and contravariance as well. Like, yeah, actually, this is not completely true. If I put it this way, compiler will not compile it. So I should make one more trick. We will see why it should be done a little bit later. Yeah, so in the case of contravariance, we put the minus sign, and like covariance seem much obvious than the contravariance. You can try to think about the contravariance, and yeah, it can play with your brain a lot. So the example of contravariance from the standard library is basically the function trait definition. So the argument type of function, the function is contravariant by its first argument type. What it means basically is that if we have any function from any to b, it will work anywhere where a to b works. Like in case of covariance, it's in another side, like it's vice versa. Like we have the subtype of like D is subtype of any, yeah. So we can use it anywhere where any works. But with contravariance, it's vice versa, and it makes sense basically. That's actually the reason why I should put here this additional type information on the push method, because the type X is in contravariant position, because this is the function basically. The push is the function, and argument X is in a contravariant position. Yeah.
What does self include?
Sorry?
What does self mean?
You mean here? Yeah, it just copy paste from the Scala standard library, so I didn't remove this. Self is basically used instead of this, like in Java.
What does it mean in this?
In this situation,
it's like tray, yeah. And what's inside it?
Yeah, that's a syntax we use instead of this keyword. In Java, we have this keyword, and this is the way we can refer to itself. Yeah, we can think about that way. The body of the trait or class is basically the function itself. This is like a, yeah, and the argument of that function is the instance, the reference to itself.
Like something in Python, where you refer to the object.
I'm not sure how it works in Python.
This is for instance
For instance, or for a trait or class?
Yes, it's self refers to the instance of class or class itself.
Well, it refers to an instance of that class. We can't refer to the class itself, because class is not an object like we can refer to. Yeah. If we speak about reflection, then it is, but basically the same way as with this keyword, if you're aware of in Java. Do you know about this in Java? Yeah, so this is the same way, but in Scala is encouraged to do that way, because that way you will not mix, you will not mess if you have a nested class or trait definition. Because when you have so, you can forget about what this correspond to which nested class. I mean, if we, let's say we have one more nested trait here, and if we use this keyword, then it's hard to distinguish which this refers to. We can lose it very, very easy. And that way we can write actually not self, but any kind of variable. It's just like a variable. Okay. Yeah, so that was a little bit out of context, but let's proceed to Scala Collections, the data structures and Scala Collection API. So here, this tree represents the hierarchy, the basic hierarchy of Scala Collection API. And at the very top, we have a traversable interface first. And the traversable basically means it represents any object that can be traversed. And for that reason, there is a single main method for each. So it means it doesn't necessarily preserve the order or something. It just says that we can apply a given function to every element. And there is, down the road, there is iterable. And yeah, you may ask what's the difference between those two, iterable and traversable. And the difference lies in the different semantics. If you look for some time at the iterable interface, it exposes the iterator pattern. And the difference is that in case of traversable, it exposes the push semantic, and in case of iterator, it exposes a pull semantic. And what I mean by that is when we have a traversable interface like that, somebody pushes to this interface. We are not doing anything, we are just supplying function, and somebody will call this function for us. And in case of iterator, we should explicitly pull elements from the iterable. We should call the hasNext and then next. So for that reason, the iterator should preserve its state because it should remember where it is in the iteration. So this is kind of more imperative kind of pattern, that's the difference. And under the iterable, there are three main types. There are sequential types, which basically have a defined order of elements and provide indexing through the apply method, so we can retrieve element by index. There is a sets, which are like mathematical sets, no duplicates in a set. A map, which is like a dictionary, a sequence of key value pairs. And under sequence interface, there are two kinds of sequences. There are linear sequences and indexed sequences. So in terms of general data structure patterns, linear sequence is like linked list. So it has a linear time of accessing value by index, while indexed sequences have a constant type for retrieving an element by index. For instance, a list that we used a lot lies under the linear sequence. So yeah, when we say that there is a linear time of accessing elements, we speak about kind of function complexity, and there is a big O notation for that. Probably you're all aware of that. So what it means basically for a given function which is associated with some number n, which in the case of programming, it's usually a number of iterations or something. There exists another function g, which is basically an asymptotic upper bound of function f. And that way we call that the function f, the algorithm that represented by function f, has complexity O n, for instance. And O n would mean basically a linear time of accessing a value in case of collection. So in terms of O, retrieving element by index from vector, vector is an indexed sequence, is O1, and from list, it's On. Are there any questions on this? Okay. Yeah, so besides this basic hierarchy, there are two different classes of collections in Scala. There are immutable collections and mutable. And all of them lie beneath these basic hierarchies that we saw. Yeah, this tree is much bigger, and this is for immutable collections. Arrows with bold represent like default implementations. For instance, for the linear sequence, there is a list as a default. For indexed, there is a vector, and there is a hash map for map. Yeah. And there is a same kind of hierarchy for mutable collections, which is a little bit bigger. Yeah, Actually, it just takes time to learn collection API. It doesn't make sense to go through everything one by one. You just need to remember these basic differences. There are indexed linear sequences, set maps, and stuff like that. Yeah, so some more interesting collection implementations for linear sequences. There is a stream. We will go through that in a couple of minutes. And linear sequences expose all of them expose these head and tail operations. And for indexed sequences, there is usually apply method to retrieve value by index. And if it's mutable indexed sequences, there should be an update operation. Yeah, and frequently used array vector, array buffer. Array is a mutable sequence vector. Vector we will see right now. So vector basically provides some interesting compromise between indexed and linear access. It is implemented using a tree of a fixed depth. So basically, we go through tree very fast to retrieve arbitrary element by index, and at the same time, it actually does it in a linear fashion. Yeah, so this is like array list in Java, basically. Yes, and for list, just to revise in memory what we used previous time, there is a nil for empty list, there is a double colon to append to list, and yes, and this kind of syntax when we have a list and brackets, parentheses, this is called the list builder, and under the hood, this is basically a syntactic sugar, because a compiler will translate it into the call to apply method. And apply method is defined on the companion object. So whenever you write parentheses in Scala, like in all places, this is actually a call to apply method, the same way as this function. When you call a function, just remember the function definition trait. There is apply method, and this is basically syntactic sugar for that. Yes, and when we use this double colon, sorry?
I have a question. What's the reason you want this functionality to object?
Well, this is how companion objects basically work. Even well, it's a good question actually, because yeah, you have a sweet. Yeah, it's a good question. There are multiple reasons, because companion object is the object which is defined in the same source file. So when you import a trait or class, the companion object is imported as well. And object by itself is kind of like a static in Java, like all methods and values which are in object are kind of a static methods and values. And this is a usual place we can do this like list builder stuff, like something like static builder operation. So this is very convenient place to do that. Does it answer your question? What?
Yeah, we can do it in constructor.
Yeah, we can do it constructor. Yes, but you can do a lot more in a companion object. It's just the way of doing a separation of. Yeah, it's like a factory pattern. You don't need to. You can think of like a factory method pattern, for instance. it's a question of design, basically. And we will see later in the functional programming, it is encouraged to separate the definition and behavior. And the same way, like logic for a built-in object, it is good to separate it, to define it separately. Otherwise, you can have a very big class and everything contained in it. This is not the functional way of doing things. We will touch it I believe, in the next lesson today. Yeah, but it's a good question. We can talk about that a lot, actually. Yeah, so this is the syntax we use with lists. When we use double colon, actually, just to better understand what's happening when we use this double colon, yes? So we have this syntax 1, 2, 3 separated with a double colon. And actually, this will correspond, this will mean the same as we would create kind of case classes, like construct a case classes. Because let's look first of all on the list definition itself. So here we have sealed trade and 2 cases for this trade. One case is nil object, and another case is so-called cons, but it is defined using this double colon. So this is a case class, and what we do here, we basically construct this nested structure, like construct these case classes. Yes, but in fact, the first definition on the screen will correspond to the third one. And you can see this is reversed, basically. And the reason of that is that all of the functions and operators in Scala which end with colon sign are treated in a reverse manner. This is called like postfix, I believe. No, it's called infix syntax, basically. So if you have an operator which ends with colon, this will be applied in a reverse kind of fashion. Yeah. And by the way, we have nothing type here, so this is like a good place to use it. In case of nil object, we have nothing to put as a type of nil, so we put a nothing type here. If you may ask where this nothing type is used, this is the place. Yes, so this is right, the word I couldn't remember, binding, basically. These ending in a colon sign, these are called right binding operators. Yeah, so about sets, sets are basically like mathematical sets, so they cannot contain duplicates. And the default implementation for sets is a hash set. And yeah, we can just to show you how we can walk through this collection API hierarchy. If you are interested in something like, for instance, what is the default implementation of set? Yes, okay, I will look up the set class, Scala collection, and we'll try to see how it is created. So I will look for the builder, which is usually in a companion object. Yeah, so, and there is a lot of stuff, but just to make you able to read that stuff, you just need to go and read it and then use to the syntax of Scala. So for instance, what we are looking for is the builder of the set, and there is no apply method here in the companion object, so probably it is defined in somewhere here in the set factory. And there is a, yeah, so there is apply method here. Yeah, as you can see, it's not that easy, actually. And yeah, so for that reason, we can do it another way. For instance, let's say I'm building a set, and I can use the, yeah. So that's the problem. That was the exact problem previous time. So let me reshare kind of this screen, and you will see. Can you see it now?
Yes.
Okay, so we will fix it like that. I will, whenever I will mirror display, I will stop sharing and start sharing again. Yeah, I think by the end of the course I will be doing it like in a second. So I should, well. You mean automatically restart sharing?
Maybe.
Okay, yeah, let's return to our stuff. So this is how you can, what I'm trying to show you, how you can navigate using the IDE through the standard library, basically. So for instance, you are wondering how this set is created, okay? I'm writing something, but I don't know how it works. So what I can do, I can hold the command or control on Windows or Linux machines and just click on the set, and the IDE will show me, okay, there is apply method here. Okay, great. So yeah, that was defined in some generic companion on the generic collection. So yeah. For instance, this syntax means that we can pass a list of values. This is like var args syntax. In other languages, it's called var args. So means I can supply multiple elements separated by comma.
The same time. For the same type.
Yeah, like in this case, because yeah, of the same type.
We can try a plus here on the definition function. I mean plus.
You mean here? No, you can. Actually, you can, if it makes sense. You mean covariance?
Yeah, and then we can use any element of drive type.
Yes. Yes. Well, no, I'm wrong. You cannot use plus here. It doesn't make sense. Plus is used only in the class or traits definitions. In case of methods, it doesn't make sense. Yeah. Okay. Let's return to our. Well, okay. Yeah, so that was about sets. And here is how maps are defined in Scala. That's how we can build them. There is such an arrow syntax, and these arrows are basically the syntax of constructing tuples of arity 2. So map in this case is constructed of 2 tuples, and each of the tuple is constructed using arrow syntax. We will, when we cover implicits, we will see how it is implemented. So this is kind of implicit extension on the left value. This, yeah? You mean sharing screen?
Yeah, we see the part window and set previous.
Yeah. Okay. Works really bad. What about now? Okay. Okay. I should get used to it. Yeah, so this is how we work with maps. And in fact, map can be treated like a sequence of such tuples, basically, such pairs of key values. And that way we can use for comprehension. There is a syntax at the bottom just to traverse through the map, through the key values of that map. Yeah, so this is pretty straightforward. And these are just common collections you may use usually. List we used a lot. Range is when you write 1 to 10. This is the builder for ranges. There is a vector and array for indexed sequences, sets, maps, hash maps, and string is actually converted to sequence char whenever you need it, but usually just a Java-lang string. So string in Scala is treated like a collection of characters. Okay, and there are these two links you can inspect in your free time. They contain a lot of different interesting pictures about the and some performance charts on collection in Scala. Yeah, so are there any questions on the collections? It's just hash map. Yeah, actually, oh, sorry. The default implementation is a hash map. I can show you. For instance, we can go to the map. I should rerun sharing. And if you are wondering what is the default implementation of map, yeah, so you can find here for instance, yeah, if you don't know, or you can go to documentation, but you will know more if you are able to read the code of the standard library by itself. So this is a definition of map, of immutable map. And if you go further here, you will see the builder actually, yeah, it's in another place, but everything starts from empty map, and then it extends to map 1, map 2, map 3, map 4, and when it's, sorry? I mean this one. This is used for serialization. Yeah. So this is the way most of the collections are, immutable collections are implemented in Scala. So you have kind of nested structures for up to 4 values. If you have a map of 4, then this implementation will be used, and will be more efficient. And if you have more than 4 elements, then the hash map will be used. You can see it is created right here. Until you have 4 values, I believe it's useful for most of the collections, such approach. And this makes sense because you don't need to instantiate the whole hash map because it takes resources, it takes memory to instantiate, it has some initial capacity and stuff like that. If you have just a small map of a couple of values or small set, then you just use this kind of existing implementation, explicit implementation, I would say. Yes, so yeah, you can inspect that later and just wander around the collection API in the standard. Yeah.
Collections for the practice.
When we will cover it? Yeah. Yeah, there will be a next class, I mean, in 2 weeks. Yeah, so, and there we will cover more parallel and concurrent stuff in Scala. Can you see my screen? Yeah, okay. Okay. That's okay. Oh, no. Stop here. Takes a lot of time. Okay, so let's quickly go through error handling approaches in Scala. So first approach, the imperative kind of approach, the same way we do this in Java, we just use a try catch. And this looks very similar to Java try catch. Besides that in catch, in a catch block, we use cases the same way we use with pattern matching. So there is a try catch, and then we use cases for different kinds of exceptions. So this is the imperative way of handling failures. Whenever failure happens, you throw an exception and you catch it somewhere down up in the stack of calls. And the thing is that in Scala, there are no checked exceptions. In Java, there are checked exceptions, and the compiler will tell you that you haven't checked, you haven't catched the exception, basically. But in Scala, there are just kind of runtime exceptions. And the reason of that is the exception usage is discouraged in the functional programming, because this is a side effect. We will talk about side effects later. So using exceptions is discouraged in Scala, basically. The try catch, from my perspective, is more like for Java interoperability. When you work with the Java API and you need to try catch it. And there is another interesting thing in Scala called option. And probably everybody of you had that kind of feeling when you don't know what to return from the method in a special case. Like, for instance, division by 0, or in the last classes we had a last function, and that last function should return something where the empty list is supplied and you just don't know what to do. So the easiest is to throw exception, but this is discouraged approach. Better approach is to use something called option. Yeah, so this is actually a way how we can express the absence or presence of the result, or just error result. You can use this instead of exception. Yeah, so whenever we have such cases, like there is something not found in database, or there is a division by 0, or square root from -1, or something like that. Oh, yeah, so we can use in that cases the option data structure. So this is just a container which describes optionality of value. And if the value of type T is present, we use a SumBuilder, which is a case class basically. We build a value, present value. And if it's absent, we use none. And the interesting thing is that when we are stating that a value may or may not be present on the type level, we are forcing other developers to handle it somehow. So we could return, for instance, a null from a method, but nobody will be forced to handle nulls. But everybody will be forced to do something with the option. Yeah, so usually you basically, you just create sum when you return something, and if there is no value, you return none. One way of checking one way of dealing with options is to use isDefined and then using a get function. But this is not very good approach, because if we missed something and we use this get will return null, and nulls are bad. Everybody knows that, yeah. So yeah. In case if like very often you would like to have something like a fallback logic, you want to get a result or otherwise return something else. So this is a way of doing this. We just write get or else in that case. Or we can use pattern matching, because the option is basically represented as case classes. So we can pattern match on option result. And this is one of the usual ways of handling options. So this is the definition of option data type. We have a sealed trait, and sealed means, as you might remember, that we can use it safely in the pattern match, and compiler will tell you if you didn't match some of the cases. And there are two cases, some and none. Very similar to list, as you might see. But in the case of list, we have a series, a sequence of values inside. Yeah, and nothing type is used here as well. There is another alternative to try-catch, which looks a little bit more closer to the try-catch itself. There is something called try in Scala, and by using that, we can wrap around some code block which might throw the exception, and this try builder will catch this exception for us and will return either success or failure. And the failure object will contain the actual exception. So this is very handy when we work with Java API, for instance, and we just wrap everything into a try. But this does not make a lot of sense when we work in Scala purely, because we can use option or something, some even better approach. Try is suited better just to wrapping around the exceptions. And if you don't use exceptions, you don't need try. Yeah, so you can use it that way very simply. For instance, converting string to integer when you are not sure if it's the integer value. So you just wrap it around, and you can do a pattern match on it the same way as with optionals. Yeah, so for instance, when you are reading from file and there is an API which throws exception, this is, by the way, how we can read something from file. We just write source from file. So we wrap around into a try, and later we can handle this result something like that. There are some of the usual functional combinators defined, like for each, for instance, or map function, which are defined on try. So we can map over the value over the success value inside. So this is about try. And even better approach is to use something called either. You can think about either like a generalization of option data structure, because in case of option, we just have none or some value contained, or some present value. In case of either, you have something meaningful on this left side. So this is very handy for error handling. This is a good approach to use this for error handling when you have the left, the error on the left and the actual value on the right. For instance, your API returns, the message returns either, and you use left part of either to describe errors and right to describe the successful operation result. And you can pattern match over it as well. For instance, the simple function of division, you just check if the divider is equal to 0 and just return left to represent the error, and you can write the error message. So this will return type either of string and integer. But on the left side, there can be anything. You can build your own error definition, like a class definition, and have something like error code in it or something like that. Yeah, so are there any questions on this? Okay, let's. Okay. I just want to quickly show you how it can be. I will stop sharing and start again. For instance, we had this last function. Oh, what's the matter? Because I have a package here. Yeah. Okay. For instance, we have this last function. So instead of throwing the error here, we can just return the left value, for instance. And then we can wrap around here into the either string and integer. Then we have to wrap the valid result into right as well. So oh, this is the recursive call, so it's already returned either. So that way, like, feel the difference. We just return integer, and the developer who uses the function doesn't know whether it will throw the error. And that way, we are forcing people who use your function to handle somehow this either result. Yeah. And you can deal with it in multiple ways. Yeah? In this case, yes. Just
variable type integer and integer, and it will distribute this with a row. And this you mean implementation of admin that someone must handle and check types.
yeah, this is the power of return type, the power of API you are building. In the case, if you return just integer value, nobody is forced to handle values of that function. Yeah. if it returns either, they are forced to deal somehow with it. Yeah, they will need, because either is basically either left or right. So yeah. Okay. Do you see my screen?
Yeah.
This one? Yeah, okay. Okay, so this is about, let's talk a little bit about the purity. This is how I called it, the purity in functional programming. And just quickly revise the definition of functional programming. Last classes we played a little bit with recursion. We knew that the function is a first-class citizen, basically a value. But there are some more things we have to concentrate right now. So this is the definition, very concise. A style of programming which aims to avoid side effects by using as much as possible pure functions that manipulate immutable data. So we have three, we can emphasize three things here: side effects, pure functions, and immutable data. And this states as much as possible. We are avoiding side effects as much as possible. And this is actually true because we cannot omit it like completely. We still have to deal somehow with, for instance, input-output operations, reading from disk and stuff like that. So in the functional programming, it is encouraged to localize all these places where the side effects should be used, should appear basically, and you localize it to the as minimum places as possible. And in the most pure form of functional programming, you just localize this place to the one place in the main method, and all your program is basically side effect free. So these are like simple examples of side effects. Some of them are obvious, some of them may not be so obvious. For instance, throwing an exception is a side effect. Print into console, drawing on the screen, this is in these cases we are modifying something outside of our program. Oh, sorry. Yeah, so if we speak a little bit about side effects, here comes some interesting thing actually, which actually might be a topic of philosophical discussion, I guess. The function, even side effect, when we say that function is side effect free, we are idealizing a little bit, because the computation which function does is basically a side effect as well. So when something is computed, the system is affected. So when we say side effect free, we mean almost side effect free. We are not treating this computation as an effect, basically. Yeah, so in a functional programming, when we say side effect free, we don't like deny doing the input-output operations to disk or login or stuff like that. We just encourage to do this explicitly, rather than in secret, somewhere hidden in the method, in between the statements of the method, without publicly declaring it. So this was about side effects. And what about pure functions? So pure functions, we can think of mathematical functions, basically. So, and there are three purity rules of the function. One is determinism, second, totality, third one, referential transparency. So what does it mean, actually? In the case of determinism, it means that the function will always return the same output when given the same inputs. So every time I call a function, it returns the same output. For instance, the plus function is deterministic, yes? And when some function returns a unit of void, in other words, this obviously means that this is not deterministic function because it doesn't return any value. Totality is basically means that function should have to be defined for every input value of the so-called domain. So here is a mathematical terminology. Basically, the function is something which translates domain A into domain B, so-called codomain. So this is the totality. And referential transparency means that calls to functions can be safely substituted, replaced by the values of computation of those functions. So for instance, if the function is not side effect free, we cannot do that because we are not sure that the state of the system will be the same, that our program will not change. If function is pure and side effect free, we can just take the value which this function produces and substitute in all of the places where this function is called. So this is called referential transparency. And you can remember the evaluating expressions that we talked last time. Everything is an expression and it is evaluated. This is just to demonstrate this is for better intuition. Pure function returns value for every input parameter. And in case of procedures, it does a lot of stuff like modifying memory, producing side effects. So we are not sure about what it does by just looking at it. So you can ask how I can do real world stuff then if I'm restricted to use any kind of side effects. So the thing is that in functional programming, it's not denied to do these operations with input, output, for instance, or modifying memory. You just need to do this explicitly. And for instance, when we changed our the definition of our last function that I showed you, we did something explicitly. We explicitly stated that this function has the effect, we can say that way, has the effect of being optional. The effect is the optionality of the value, basically. That if we did it with options, and the same goes with either, basically. So this is kind of effect of potentially returning the error value from the method. And there is another things, or another kinds of effects we can talk about in the functional programming. We will not cover this today. For instance, future tasks, there is something called I/O for dealing with input-output operations. Yeah, so this was about pure functions. And the third statement, we use it in our functional programming definition, immutability. So this is going to be simple. Like, if you have mutable state, you should deal with that when you write the concurrent and parallel programs. You need to manage somehow this change in state. So it adds a lot of complexity to our programs. So this is why immutability is encouraged by the Scala language design. And we can have immutable values. We can have immutable data structures, like instances of case classes, which are basically containers of values, of immutable values. And there are immutable collections. So whenever we want to use something, in the first place, we think about immutability. So all this seem like a lot of restrictions, actually, a lot of constraints. But one smart guy said that liberties constrain and constraints liberates. There is a link on this slide to the video by one smart guy. You can watch that video. Really, a lot of smart ideas. And the benefits it buys to us, the thing is there are a lot of benefits with these constraints. For instance, first of all, equational reasoning. So we can, whenever we call a function, we can substitute it with the value of that function. So we can reason about our program. We are sure that nothing bad is happening under the hood. So this comes to more predictable results of the program when we use immutable data structures. And when we isolate places where the changes occur, this goes like a straight safety by design. Yeah, so let's make a break right now. Yeah, nice. Що там до речі, я, мабуть, зрозумів. Та нічого, я вже, в принципі, зрозумів, в чому проблема, мені підказали студенти. Це от. I will resume the recording, and you will tell me whether you can see my screen. Can you see my screen shared? Yeah? Everything is okay? No? Okay. Sorry. Yeah. Nice. So let's talk about functional primitive. So this is something that I call it like that, like the primitive patterns and structures of functional programming. And oh, sorry. So let's just revise once again how the function definition look like, this function trait. So we actually already covered that, but this apply method on the in this trait, this is how the function is called. So whenever we have these parentheses, the apply method is called, and this goes not only with function but with anything else as well. Yeah. So this is the function application basically. And higher order functions, this is whenever you use map or flat map or any that kind of combinator on the list, you use higher order function. And by that, it means just a function which takes another function as a parameter. This is called higher order function. A map is a higher order function. Yes, so there are just a few examples on the list. And the thing is that, for instance, 5 years ago when I started to learn Scala, this was something very special. I hear some echo. Sorry. This was something very special for me, this higher order function and all this functional API, but nowadays it exists in most modern languages. So this should be pretty obvious to you, I guess. I hope. Yeah, and this is how we define the higher order function. This is basically the equivalent of for each method on the list. We just define the argument of a function at the function itself. Yeah, and instead of this syntax of function type, we could use the function one of integer and unit. This doesn't matter basically. This is a syntactic sugar. Yeah, and more than that, more than being higher order function, these are polymorphic functions, as you can see. And you might notice this method compose and then on the function interface. And this is this is something that we talked about last time. So we build the a functional program from the smaller pieces. The smaller pieces are functions, and we compose them. So this is about modularity of our program. So if our program consists of smaller pieces, we can modularize it very easy. And the composition itself is, for instance, you have two functions f and g, and when you apply two maps in a row, for instance, on the option, you map with the function f and map with the function g. This is the same as stating that that we want to apply f and then g. So this is the method call on the function f, and this basically means the same as we call function g first, no, function f first, and then the result of that call we wrap around with the function g. So this is called composition. This is pretty obvious, I guess, but the method compose can be a little bit confusing sometimes because it works like in a reversed way. It should be read in a reversed way. With and then method, you just write f and then g. This is very obvious, yes. And with the compose, you should think about it first. So you should, in the case of compose, you apply function f first, and then g function will be applied around the return type of the f call. Yeah, so this is called composition of functions. Another thing called carrying, and there was a guy named Howard Carey, which invented a lot of stuff in functional programming. And this is something that I can't remember who, but somebody asked last time about this syntax with multiple parentheses, multiple argument lists. So when we define a function like that, wrapping the argument, each argument in its own set of parentheses, we define the function, the carried function. This is a carry syntax, basically. And the thing is that we can apply such function partially. We can supply only one only the first argument, and this will return a function which with the one argument, basically. This is called carrying, basically. Yeah, and there is something called partially applied function in Scala, which goes hand in hand with carrying. So you can partially apply arbitrary function, not just carried function. And this is one more usage of underscore symbol. Like, for instance, we have this add function, and we want to produce the function which takes only the second argument, and the first argument is already kind of supplied, yes? So this syntax will return such function. This is, yeah. So you can do it with arbitrary number of arguments with that kind of syntax. Or you can write it like define a separate function with the arguments and then apply them explicitly. Yeah. And there can be a confusion, and this is something which people tend to ask on interviews for a Scala position. What is the difference between partially applied and partial function? Yeah, so partial function is completely another thing. So partial function means that we can define, this is a separate interface. This is not a function one, function two interface. This is a separate definition of separate kind of functions. Yes, this is basically a separate kind of function. So whenever we want to define our function not on the whole domain, remember we spoke a few minutes ago about domains. So function is from domain A to codomain B. So when we want to define a function which works not on the whole domain, but on a set of exact values, we can use the partial function. For instance, this function works only for value, supplied value 1. And if we supply value 2, it will fail basically. And there is a method defined at to check whether a function is defined on such for such argument. Yeah, you may ask what is the usage of such partial functions, and one of the usages from the standard library is the collect method on the list. So collect method wants the partial function as the input, and we just define which elements we will collect from the list and which we will skip. And you can chain partial functions like that with the or else syntax. Okay, are there any questions on this?
In the lowest chain, where are the parameters for those functions?
In this chain?
Yeah, it's like df1 is a function.
Yeah.
So we should call, if it is a partial function, we should call like with some input.
No, it's just a function as a value here. We are chaining these functions, and the thing is that the result of this expression is a function as well. And this is a partial function as well. And if some argument will be supplied to such function, this will go through the chains of these cases.
And then we can call this like from the dimension.
Yeah, you can supply it as another partial function. This can be useful in some cases. Yeah, so another topic which I would put under this functional primitives is lazy evaluation. So just let's go through the regular flow of evaluation expressions in Scala. So whenever we supply something to a function, the first thing that is done, the arguments are evaluated. For instance, in this case, 1 plus 1 will be evaluated first and then supplied to a function. And this is something called eager evaluation. And most of the languages are eager evaluated by default. So when you supply something, that expression is evaluated first, and then the value is passed as an argument. And another name of that is call by value strategy. And there is another thing named call by name in Scala, and there is a special syntax for that kind of argument. So whenever you want your argument not to be evaluated right in the moment of passing to the function, you just add this colon. So this is kind of like a function kind of syntax. And the thing is that the arguments will be evaluated on the first usage of them. And if they are not used at all within a function, they will be not evaluated at all. This is sort of passing the functions basically, but this is just more convenient syntax, I would say. Yeah, so for instance, we can have recursive calls like that as well. So this is called lazy evaluation. And for instance, in Haskell, everything is lazy evaluated. So any expression will be evaluated only when required, basically. So that's the difference between strict and non-strict evaluation. Yeah, and there is something called lazy val in Scala besides regular values, and the difference is kind of the same as with eager versus lazy evaluation. The lazy val will be initialized on the first access to it. So the body, the expression of this lazy val definition will be evaluated on the first call to it, and then on the subsequent calls, there will be this result of evaluation will be kind of cached, basically. You can look in this example to see what happens here. So we have a body, a block of code, which prints something to the console. We can just test it. So on the first access to it, the print will happen. On the second access, print will not happen. This is very useful when we define some heavy computation and we don't want it to be evaluated right now.
Okay.
Yeah.
Question is about how it is stored in the memory, like when we declare well equals 2, it's just someplace in the stack with the 2 value. But if we declare lazy val 2 plus 2 and we pass it somewhere, so it's like in the stack it must be some instructions with 2 variables. So
well, actually, under the this is a syntactic sugar again. Under the hood, this will be compiler will create a method basically, and basically a mutable variable under the hood. I guess so. We can refine it, but yes, there will be a separate method, and that method will be called on the first access, and the resulting value will be stored in the variable. This is how it works.
So if I just use lazy val for 2 plus 2, it may be more consuming than just creating the value equals 4 if I don't need this lazy evaluation.
If you don't need
Because
lazy
it will be
evaluation,
just one more function that will be passed everywhere. And
no, it will not be passed everywhere. Just it will be called only one time. So, in terms of resources, I would not say so. Just the one more function definition is a little bit more memory in the so-called perm generation. Like, okay, this is another topic, but it's not a big deal. If you have a simple value, yeah, just use values. If you need to compute something lazily, and the thing is that we can use it in the recursive calls. We will see in a moment. Yeah, so for instance, when there is some computation which may produce errors, like in our famous rational trait, yeah. For instance, when we define the numerator and denominator, the g can be supplied can equal to 0, yes, and in this case the whole thing will fail. But as they are defined lazy, they will be not instantiated until at least the class itself is instantiated. Yeah. this is one of the cases we could use it. So, okay, that was a good question. I just forgot about my sweets. Sorry about that. Yeah, this is first time we use this stream word in this course, at least in the Scala part. So stream is basically a data structure the same as list. It's a collection basically, but the special thing about that is that every value in it is lazily computed. So, for instance, you can have infinitely long stream. For instance, in the second example, we recursively define the infinite stream, and it will compute only the time when we take values out of stream explicitly, and until then, this will be like a stream with one value, and that's it. For instance, this is an explicit syntax to define the stream of natural numbers, stream.from1. And this is how we can define a stream of squares of natural numbers. Very easy. Yeah. And you can do wherever you want with these functional combinators, filtering, mapping. And again, every time the computation will not happen until we take values out of stream. And this is the way we can define prime numbers. Very concise way of getting the list of prime numbers. I would say one of the most concise syntax ever. Yeah. Sorry? From? Yeah, so from is the syntax of defining the infinite stream of natural numbers. Well, when we say stream.from1, the stream of natural numbers is created, but it is not computed. It contains only the first value, 1. And then everything else will be computed on the request. Let's say so.
So just after we write tape, then we
when the computation happens.
everything.
Yeah, the computation happens when we write tape. For instance, this map function will not happen on the value 2 until the take happens. So at the moment the take happens, there is a chain of function calls, and for value 2 is retrieved, and then map function is applied, and so on and so on.
But what happens when we try to take again? Then the whole computation will happen again, or there is some buffer inside that would take some values computed before and store it?
I'm not sure I understand. Can you?
Okay, so when we write square take 10, then we can write another square take 10.
Yeah, no. At that the second time it will not be. This will be cached kind of. Okay. Oh. Yeah. So this is how we can define prime numbers. Very easy. This is a recursive call. So you can use recursion with streams that way. What we do here, we just filtering out all of the numbers that the same way as a how it's called, a route span approach or something like that. Just filtering out all of the non-divisible numbers. Yeah. So this is very concise, and first time I saw it, it was like this picture. And this is some simple assignment for you to implement stream of Fibonacci numbers from A to B. You can, the usual way, you can just post in Slack, whoever completes. Are there any problems, ideas? Okay, so it takes a little bit more time than I expect. I will post the oh, sorry, that was the wrong one. Let me, yeah, so this is the implementation, very simple implementation, basically. Yeah, I know it can play with your brain when you think about streams and lazy computation. So what do we have here is basically the yeah. This is the same kind of operator like with list, but is used with streams. Yeah. Yeah. So there is a recursive call, and what we do here, we just add in the numbers to the stream, which are sum of the two previous numbers. So when we add one more element, the fib from produces one more value, and this value is basically the value of sum of previous two numbers. Okay, where we are, we can do it even in case of Fibonacci numbers, even more concise, I would say. Yeah. Okay, are there any questions on streams? Okay. By the way, I forgot about that was you asking a question. Yeah. That was you. Okay. Here we go. Oh, sorry. Yeah, I should. rehearse this one. Okay, let's switch to more interesting stuff with full comprehension. So consider this example. We have a case class of person, which has a name, which can be female or male, and it has a children, which is a list of person. And what we want to do is basically to filter, to find out names of mothers and their children in the list. So we can do this with the functional combinators like that, basically filtering whether it's female and then returning the children of that person. So this looks okay, but actually it's a little bit hard to read this kind of expression with all these filters and flat maps. So we can do this in a more concise way using full comprehension. And remember, in full comprehension, we can iterate through the collections, we can have filters with if, and we can yield values. So it turns out actually that Scala compiler will translate this syntax to this first syntax, basically. So this full comprehension actually will be translated in a series of filter, flat map, and map calls. So this is what full comprehension means actually in Scala. This is another kind of syntactic sugar.
So we can continue with different filters and so on.
Yeah. You can essentially what is the structure of full comprehension? You have a sequence of generators, definitions, and filters, which is denoted with a sequence, and yield some expression. So in case of in this case, this is called generator, this is called definition, and this is a filter. And you can as well enclose it in the curly braces. This is I would say encouraged syntax, but this is just one line syntax. And in that case, you can omit the ending sign. I forgot the name of that. Yeah, you can write in a multi-line. But there is one thing: the generator should become the first in the sequence of these statements. You cannot start full comprehension from definition or filter. There should be a generator. And yeah, so this is how the generator, definition, and filter looks like. And when you have one generator, this kind of full expression will be translated into a map call. This is the same as mapping through the list. And the thing is that you can use it with, for instance, with the option as well. Option has a map function on it. And if there are two generators, there will be a flat map call and a nested for expression, which will be in turn translated into a map call. So this is how this series of maps and flat maps translated from the for expression. And filters will be translated not exactly into a filter function, but with this filter function. And this is something about chaining operations on the collections. For instance, if we have multiple filters in a row, every call to the filter will be a separate traversal of the collection. So this is this has a performance cost. And with filter operation, we'll stack these filters and we'll call it, we'll make it like a single traverse through the collection. So this is how the filters are translated. Every if statement is translated into this filter call. Yeah, and you can as well have a patterns here. The same way as with values, you can have a tuples on the left side, and they will be basically pattern matched from the expression on the right. This is the translation syntax of this one. And the definitions are, it's a little bit weird here, and it takes some time to understand. So definitions, every definition will be translated into the nested for loop with a tuple on the left. And you can notice that expression 2 will be evaluated every time for every x generator from expression 1. And this is a bad thing because, well, because we don't need to generate, to re-evaluate it every time, because expression 2 doesn't depend on expression 1. If it, in the case if it doesn't depend, then it's a bad idea. So, in other words, for comprehension, you read the best the cases when we have a series, sequential, a chain of computation, which every computation depends on the previous one. So kind of for sequential computations. And again, map, flat map, and filter functions are defined only not only on the list interface. The types that we saw today, option, try, have map, flat map as well. So we can use them with a for comprehension as well. Yes, and if we omit the yield keyword, then this will translate into a for each call, because for each just doesn't return anything. We just apply some function. Yeah, and there is a method in the Scala library which can produce the output, the translation output of for comprehension into the series of these function calls. So you may think about the common interface which satisfies the for comprehension that can be used within for comprehensions, and this could be can look something like that. So there is a map, flat map, this filter or filter, and there is a for each. So whenever we have a class of objects which have these functions defined within it, we can use that object within for comprehension. And as I said, not only list, we can use it with options as well. So this is very convenient way of dealing with options or with others, for instance. Whenever we have, for instance, we have all of our APIs returning properly error-handled results with options and others or tries. So this is the way we can deal with that very easy in a declarative way. So in this context, we are not dealing with the option itself, we're just retrieving the value out of it, because we are not interested in dealing with the option, we're interested in the value inside it. Yeah, so either it cannot be used out of the box like that, because in the case of either, when we are mapping, we should state explicitly on which side of either we are going to map. because either can have a value on the left and on the right side, yeah? And when we are called map function, we don't know on which side of the either it should be applied. For that reason, there is a either right projection and left projection. And when we call right method on the either instance, this produces kind of right biased either. So all of the functions like map, flip map for each will be dealing with the value on the right. And that way we can use either within for comprehension as well. And this is very convenient way of dealing with error handling. You just define all of the methods returning eithers and then using within the for comprehension. So that way we kind of abstract over this context of either, list, or option. We're just dealing with the values inside of this context, or in other words, affect. We can say like that as well. Okay, so are there any questions on for comprehensions? Yeah.
Question about either. We have right side and left side.
Yeah.
As a local function, when we don't want to catch any exceptions, so we are working on only on the right side. But what we will do if we have, for example, some errors on the left side. So what we are doing with this errors streams, or do we just log them, or collect them as any
You can do wherever you want, actually. You just, yeah, one way is to construct, to build a list of those errors or something. Another way is to log just when they happen. The thing is that we are returning them and we encode this into the API. There is some other types for dealing with errors as well, because either is a little bit limited to that, but it is from standard library. There are third-party libraries which provide more convenient error handling data structures. So for instance, chaining all of the, collecting all of the errors into the list. And then an error can be not just string, it can be any kind of object you define on the left side. And essentially, it depends on the approach you want to your error handling. In some cases, you want to collect errors. In some cases, you want to fail fast, like error happened, and yeah. And in this case, for instance, if there will be a left at some point, for instance, in this case, we have a right. Here we use the right biased either, so we map on it. Actually, the flatness in the whole. And in the case of either two, this is the left. And when we have the right biased either, this will fail fast, basically. So this is what return the E1, and E2 will relate the whole thing to the left, actually. Well, let's just try it. So
when you're executing, is it to right or it returns?
You mean this one?
Yeah.
This returns type named right projection. But when the function is called, like here will be a map call on this value. This value is left. And when we call a map on the left side, it will basically return the left again, because there is no value on the right side if you want to map on. So essentially, in this case, the left value will be returned here. You can.
What will iterator do with string? If it writes like it discharges?
Okay, let's just return to the, you know what, let's just inspect in the IDE. So, for instance, oh, why can I? Well, I cannot copy from here for some reason. Okay, so for instance, I have for comprehension retrieving one value from the right value. This is a kind of error result. And I want to return the, well, to make it more obvious, let's make it that way. Something like that. So these are values, just to imagine they are returned from some method calls, yes? And I want to deal with the value, with the results of the those method calls, to deal with this either type. And one thing we can do here to understand what's going on, we can just add type annotation here. So, oh, sorry, I need to make it explicit. Yeah. Okay. So essentially, this for comprehension will translate into the chain of flat map and map. So this is the correspondence. You can check actually. Yeah, let's run this. Oh yeah. Okay, so as you can see, it produces the same result. Yeah. So this is the same, the for comprehension syntax and the syntax with function calls. This is exactly the same syntax. The compiler will translate the first one into the second one. And yeah, and you can see that this evaluates to the error because we had either two on the left side, so kind of error state. And we cannot map on it because having the right projection, we are mapping only on the right side. Is it more clear or still unclear? Okay. So you can do the same thing with options. For instance, when I say
If you're calling it the one right, saying on which side of the picture you want to iterate.
yeah, exactly.
And in the second case, there is no iteration.
There is no iteration because this is, to better understand, let's do the same with options, kind of the same, yeah? So there are two option values, and I'm trying to iterate through options, yes? Yielding some result O2. So yeah, it evaluates to none, because it cannot map over the none. Map over the none returns the none itself. Well, it can, but it just returns the same none as before. The same with the left side. So we can have a left biased either as well, but usually the usual pattern of using either is for error handling, and with the error handling we have error on the left side and the valid result on the right side. Yeah. Okay, I hope this was a little bit more clear. Yeah, so you can imagine your API well constructing with that kind of context, options or eithers. You can deal with that with 4 comprehensions in a very declarative style. Like pretending there is no such context at all. There is no option, there are just method returning the values. It will look like that. So here comes the monad. And yeah, this is can be a face of the people that constantly hearing this word. And I must agree, this is not the best sounding word for such a beautiful thing, actually, like monad. And here is the thing: wherever we have a map, flat map, filter, and something called unit, we have a monad. So any kind of object which satisfies this contract, and by saying contract, I mean interface, basically, this can be called monad, almost. And unit is basically the kind of null value of the object, of this particular object. In the case of list, this is a nil empty list, yeah. In the case of option, this is none. In the case of either, well, in the case of either is not completely that kind of thing. We should speak about right biased either or left biased either. In a case of try, this can be a value, but try is not exactly monad actually. So we can think about option, list. So and any other kind of object which had this contract can be used within 4 comprehension. And but to name it a monad, there is one more thing that should be satisfied as well. There is something called laws. And right now you can think about mathematical laws like associativity, commutativity, yeah. And in the case of monad, there are 3 monad laws. You can see like here. So when we have a unit, or kind of null value of a monad, and we are flat mapping over it with some function. This should equal to basically applying the function to the unit value. Well, sorry, I was wrong about the unit. I was thinking about another construct, not monad. So unit is basically applying the context to some particular value.
Sorry, what is C of A and of B in square bracket? Like unit?
It just...
It has an input of A of type A and returns.
You mean this?
Yep.
This is some arbitrary interface which satisfies this contract.
C is an interface.
Yeah, I mean, this is, in this case, this is just to build an intuition. Like, we have this kind of methods for the option. And in case of option, we should put option here instead of C. So for any arbitrary type C, which satisfies this contract, we can speak about monads in the case of that type.
It returns something that depends on A, on type A.
Yes. For instance, just think about list, yes? When we map over the list of type A, of values of type A, we return the list of values of type B, because we apply function from A to B. Okay. Yeah, so the unit itself, it's not that kind of null value. Sorry about that. I was thinking about monoid. In a monad, it's just the constructor, basically. You can think about apply function that we discussed previously. This is a way of putting something into this context. In case of option, it's a sum builder. In case of list, it's a list builder, and so on, so on. So, monad should satisfy particular laws to be called monad. So, objects that that we want to call monad should satisfy these laws. Left identity, right identity, associativity, and this associativity is basically the same as with a, for instance, plus function. You should just get used to read this syntax. For instance, yeah, left identity, when we apply flat map on the unit, this is the same. This should be the same as applying f to the value x directly. So, for instance, just to provide example, there will be better intuition. This is the same issue. Okay. Sorry. Then I will switch my display. Okay, never mind. Okay, so this is the example with the list, and we are speaking about left identity. In the case of left identity, we basically have a list. We are building a list of one value. We are applying a function with a flat map to that value in that list. And this should be the same as just directly applying the function to the value. Oh. Yeah. I should automate that somehow. Yes. This is what I'm speaking about. This is left identity. Right identity is should be pretty straightforward as well, and associativity the same way as with a is a plus or multiply functions. Okay, so this is about monad laws. Share it again. So the common use case, as with the for comprehension that we saw, the common use case of monads is kind of chaining operations together. When we have some operation and another operation which depends on the result of the first one. And this provides this interface of chaining them together. So basically sequencing the operations. Yeah.
Extracting the sublist right in the common list, but why we don't use this map?
You mean in which case?
In the case of monads, I mean, why we should use the, why we should have flat map but not the map? Because the functionality is pretty similar. It's like exploding.
Well, it's not similar. It's not similar, actually. For instance, let's speak about lists because we used to them. So if I have a function, list of list of let's say integers. Yeah. So if we have a function from integer to string, yeah. We can apply it using map, and we will return a list of strings. We will return a list of strings. Okay, but what if I have a function from int? No, okay. This was short. Oh, this is better. Thank you. Okay, so what if I have a function which produces a list, actually? What I will do with that, for instance? From integer to list of strings, yeah? Having only map function will not help me because I will, in return, I will receive something like nested list, yeah? List of lists, yeah? So this is the matter of existence, the reason of existence of that map. So what I'm doing, I'm mapping and then kind of flattening this structure, because otherwise I cannot deal with this nested kind of thing. So that was something I should ask you first. Everybody is clear with the flat map function. Is it okay right now? Okay. Yeah, so the flat map operation is essential when dealing with such things, such contexts, such containers like collections, because not just list. Most of the collections expose this map flat map interface. Yeah. Yeah, so the thing is that in Scala standard library, there is no such thing, no such interface like monad. If you try to search it in standard library, you will not find it. And yeah, there are multiple reasons behind that we can speculate about. So yeah, so from one point, this could be overwhelming because the definition of monad can be too complex. And from the other perspective, the monad itself is such an abstract concept that it's not needed to include in a standard library at all, but still everybody uses it. And in fact, in other languages, whenever you use map, flat map, yeah, you're basically using a monad. This is a kind of a monadic transformations. This came from functional programming, but everybody uses it. Nobody knows about the monad. Yeah, this is the thing. And for that reason, in Scala world exists some third-party libraries which implement all this stuff like monad and so on. And well, it was saying that the monad, the definition of the monad as a concept came from category theory. Category theory is a field of mathematics. And besides monad, there are a lot of other stuff. There are applicatives, monoids, foldables. Basically, take any method from the list interface or from the collection interface from any modern language, fold left and stuff like that. And everything, this method is represented somehow in terms of category theory and a pure functional programming. But the monad is kind of the most used, I would say, and the most important to understand first. Okay, so are there any questions?
Regarding monad and generic programming, so as understood, in those third-party libraries, we have an interface for monad.
Yeah.
And like original question was, we could restrict our generic function arguments to be in some kind of like hierarchy. I mean, it should be a superclass of that class, or it should be derived from any ref, for example. But is there a way to restrict it to monad, another case, not to class hierarchy, but to class rate?
Yeah, there is a way. There is a way, and we, if there will be enough capacity today, we will go through that, some of the patterns that are used in those libraries, and they enable monad implementation. Yeah, there is something called type class. There are implicits which enable us and enable these guys to implement all this stuff, because you can do actually almost everything in Scala. Syntax is versatile. Yeah.
That was a good question.
Okay.
About the capacity to not elections after, I mean, what do you mean by capacity?
You mean, I mean, the time, if time left, if we will be able to go through all of the material? I hope so. By the way, how much time do we have? 3 minutes. 3 minutes? Oh, okay. Then, yeah, we don't have any capacity left. Okay. Okay, we will quickly go through the unit testing because this is pretty straightforward subject. you can actually do that while working on the home assignments. Yeah, so while this screen, okay, screen is shared. So there are two main test frameworks in Scala, Scala Test and Specs2. This is a unit testing frameworks. You use to write unit tests. There is a Mockito for mocking objects. There is a Scala check, and Scala check is about property-based testing. So this is how we write the usual unit test using Scala test. So this is very declarative. This is how we can edit dependencies, and the usual. This is how usually the test looks like. Very declarative, I would say. And yeah, the interesting stuff is property-based testing, which is Scala check is all about. So let's think about this plus function, and again about mathematical properties of that. So it should satisfy associativity, commutativity, and just think about how we could test it. Because usually in the usual unit testing approach is have some input data and have some output data. Basically asserting that the function with this particular input data equals to this valid output data. But what if we want to test the associativity itself? It can be not enough just, this is just a one input, one set of input. And in the property-based testing, we are testing not the inputs and outputs validity, correspondence, but basically the properties of the function. So just think about, we could generate a number of inputs and just check if the associativity rule holds. And this is what the property-based testing is all about. So we can, in case of list, for instance, we can think about the sum function on list. So sum function satisfies that list of properties. For instance, the sum of the empty list is 0. So we can, yeah, the sum of the list whose elements are equal to x is just the list length multiplied by x. So this is the kind of a property we can think about. And in a Scala check, yeah, for instance, our famous rational example. In this case, we can test the logic of reducing the minus sign to reducing it to the numerator. For instance, if the denominator is supplied as a negative value, we will put this negative value into numerator. We can test that property by basically generating a lot of input data. This is for all. This is named generator in Scala check, and it will generate a lot of pairs of integers basically. And then we can check the property that while the rational number is created, this satisfies the set of these properties of, for instance, if both values are less than 0, then the nominator should be positive value. If both are negatives, then this negation reduces. So this is the property, basically. And for instance, with the monadic laws, you can use Scala check to test them as well. Yeah. Oh, sorry. We should definitely do something about that. Mm. Okay. So you have lost me somewhere here, probably. Yeah. Oh, you missed the whole property-based testing section. Where you lost me? Sorry? Okay. Okay. Okay, that's okay. So, yeah, there was something I wanted to share on functional design. So we will cover this next time. And basically, something somebody asked me a question on this: how we how it differs in classical object-oriented versus functional design. And in functional programming design, we tend to separate data and behavior. Yeah, and there are interesting related concepts around functional design. And there is a section on implicits. Yeah, so that's two main sections we are late to cover today. Okay, thank you. This is all for today. Thank you for coming.